In this video, we'll be discussing how we incorporate Latin squares designs into analysis using the R statistical software. First, we're going to talk about how we can actually use R to select Latin squares designs. I'm going to begin by installing a package called Magic that'll allow us to use some built-in functions that can create Latin squares. Going to go ahead and load this up into my library. Now if I just try doing Latin 4, you'll note that this gives me a random 4 Latin squares design. Note what's going on here. Each of these, instead of being letters as they were in our textbook and in our slides, are now going to be numbers within. So it's important to track that this would represent treatment number 1, treatment number 4, treatment number 3, treatment number 2, while each of the columns is still representing 4 levels of the blocking factor 1, and each of the rows is still representing 4 levels of the blocking factor 2. For the rest of this video, I'm going to use a set seed so that we can all stay on the same page. I'm just going to kind of make up a number. How about 48984? Now what this should do is, as we generate designs from now on, let's say I do Latin 4 again, this should keep us on the same page with what is being generated. All right. So now we're going to be using a random Latin square, and how we select a random Latin square is to use R Latin. So we'll again do size 4, and if I run this command twice, you'll see that I get a different random Latin square. We're going to be using this as our starting place, just like we mentioned in the slides, for designing our random Latin squares design. What I need to do is save this, so to make sure that my set seed is still applied, I'm going to run set seed again. And then I don't need to run this line again, but I guess I can. And then I'm going to save this Latin squares. I'm going to say LSDES for Latin squares design to save that random Latin squares so that I can call it again. Note that in R, if I save a random value, it's not going to change every time I run it. It's going to stay constant, which is one of the reasons that I save it as a variable. Now remember that we want to randomize the rows and the columns, and how we discuss this is we're going to randomize all rows except for the first one, and then we're going to randomize all of the columns after we've randomly selected a 4 Latin squares design, a 4x4. So this was our random selection of the 4x4. Now we're going to randomly arrange the rows. And we said that we want to keep the rows in order, but then we want to randomly select something that goes between 2 and 4. So I want to randomly arrange these bottom 3. So my new order is going to be the number 1, but then I'm going to sample from, let's say, 2 to 4, a number that's going to be selected. So this is going to keep the number 1, so 1 stays the same, and then it's going to arrange the numbers between 2 and 4 in a random order. So if you just run this code, it's going to undo my set seed, but that's fine. I'm going to get 4, 3, 2 would be the random order. If I ran it again, I get something different and something different over and over again. Now because I just undid my set seed, I'm going to go back, run my set seed again, and then just keep hitting Control and Enter at the same time until I've run my new order. My new order for the rows should be this. So if you're following along on your computer, this is what you should expect to see with an updated R. So I'm going to go on and change my Latin square design to be my original Latin squares design, but now I'm going to arrange the rows in this new order. So now if I look at the Latin squares design, I can see that the rows have been rearranged such that 1 stays the same, but the second row has now gone to the 4th slot, the third row has now gone to the 3rd slot, etc. All right, so now I'm going to randomly arrange the columns. And in this case, my new, and maybe I'll write this as new column order so I don't get confused. Maybe the last one should have been called new row order, but that's okay. I'll randomly sample between 1 and 4. So my new column order is going to be 4, 1, 3, 2. That is, I'm going to take the fourth column, and that's now going to become the very first one. So I'm going to move from 3 all the way over to 4. The first column is going to be in second place. The current third column is going to stay in third place. And the current second column is going to move to fourth place. So let's go on and switch this up. ls underscore des moves to ls underscore des. And then I'm going to do comma new column order. So remember, row first and then columns. So to rearrange the columns, I'm going to put the new column order second. And then look and make sure, okay, so the fourth column, that was 3, 2, 4, 1, should now be the first column, 3, 2, 4, 1, and it appears that that's true. So you can go on your computer and double check that that happened appropriately. And this final value is our new Latin squares design. So this is our randomly selected Latin squares design. Recall that in this Latin squares design, this is going to be our randomization order. So this is going to be how we have selected our particular Latin square for how we will run this analysis. Also recall again each of the rows and the columns, so each of the levels of the column, each of the levels of the one blocking factor will be a column, and each of the levels of a second blocking factor will be the row. And each of these numbers don't represent data, they represent which treatment level you're doing in which spot. So in this case, for the treatment, I'll be doing the third treatment level with the first level of blocking factor, the first level blocking factor 1, first level blocking factor 2. I'll be doing the second treatment level with the first level of blocking factor 1 and the second level of blocking factor 2, etc. So this is how we select, and again, for the design component, this is the tricky part. This is the tricky part, doing this and then running it. The analysis is not particularly tricky. So for us, let's go on and practice the analysis. It's not going to be too bad. We're just going to make a random data set here. I guess I'll just make a data frame. So let's say, I know in class we talked about doing a driveway example where we're talking about applying different levels of treatment to different driveways. So let's make a driveway. So let's create a factor. And we'll just go 1 to 3. So driveways from 1 to 3, and we'll just repeat each one 3 times. Now for our Latin squares, we need a second blocking factor. Previously, we talked about using an operator in some of the previous videos, so let's try that as factor. And I'm going to, again, repeat, I'm just going to use numbers here. I'm not going to try to do words, and in this case, I'm just going to repeat each 3 times. Not repeat each one 3 times, but repeat the entire vector 3 times, and you'll see how that turns out in a second. Now using my random row, this is how I assign where each of these treatment goes. How do I assign each of these treatments to the different driveway and op conditions? So actually, let's go on and run this data frame just so that you can see what's going on. I'm going to add another parentheses here, and then I'm going to just do Control Enter while highlighting that. You can see that this first column, this is the driveway column, the DW column, is being run as 1, 1, 1, 2, 2, 2, 3, 3, 3. That this second column is being run as 1, 2, 3, 1, 2, 3, 1, 2, 3. So this creates all of the unique combinations between my rows and my columns. Normally what we would do is we would write this as a table and then put our data in, but when we enter our data in, typically we enter it the long way, so that's what we're doing here. And I'm actually going to use DW equals and OP equals because I bet that'll make this look a little bit prettier if I run this. Oh yeah, way prettier, DW and OP. All right, so now I'm going to delete that extra parenthesis I added and do the treatment. So again, this treatment order, that is what treatment level goes with DW1 OP1. That could be done via how we did this blocking factor. Which treatment level goes with the first level of the factor 1, the first level of the blocking factor 1, the first level blocking factor 2. In this case, it was treatment level 3. Now we have a 3 by 3 in this case. We could do that. I've already gone ahead and done this, and the order that I came up with was A goes with the first driveway, the first operator. B goes with the first driveway, the second operator. C goes with the first driveway, the third operator. C is going to go with the second driveway, the first operator. A is going to go with the second driveway, the second operator. And B is going to go with the second driveway, the third operator. So that's how we're going to look at this. And that's one way that you can think through what this order means as you're writing out your different values. Now in this case, we're going to look at the different damages done to the driveway, and this is observed. So all of this up here is part of our design. This is our design component, how we're doing each of the treatments with each of the driveways and each of the operators. This is the design component. Now after the design component, this is that step 1 through 3, I think it's step 4 where we say choose your design. This is that design component, and we have to do all of this, and we can do all of this at that point. Now, after we've done that, we actually run the experiment. So right here is where we're at before we run the experiment using our randomization and the randomization we did above. And now we see what happened. So when I observed the treatment A with the first driveway, the first operator, I found a damage of 8.7 on the damage scale, whatever that damage scale is. When I looked at the first driveway, the second operator with treatment B, I found a damage of 3.6. When I looked at the first driveway, the third operator, which was treatment C, or which was paired with treatment C, I found a damage of 5.5, and so on. So 4.6, just typing in the rest of these damages, 6.8, 4.7, 5.8, 6.2, 7.7. So let's count these, 1, 2, 3, 4, 5, 6, 7, 8, 9, perfect. And now if I run this and I look at my DAT, I should be able to see exactly what we were talking about earlier. We've got the damage, we've got the driveway, the operator, and the treatment that's associated with them. So for driveway 2, operator 3, we assign them treatment B, and we observed 4.7 damage, and I'm just going to keep it as damage. All right, so now that we have our data typed in, we can go straight for the analysis. Model, AOV, we're looking at how damage was affected. Now, note that previously what we did is we had the treatment, and then we added in the blocking factor. But now we've got 2 blocking factors that we need to add in. Now in R, it's literally just as simple as pressing the plus key and then adding another blocking factor. That's all it takes to add in another independent variable into your model. So blocking factors are going to be our factor variable. Now these are our blocking factors. In R, it doesn't separate between blocking and independent. Remember, what we're just going to do as the difference is for the blocking factor, we had the restriction on randomization, and we're just not going to read the statistical output related to that blocking factor. And we'll call our data as DAT. So now we could go on, we could write the summary of the model, but we're not going to. Remember, we need to check assumptions first. So with all of these things, it's very important to, at first, check your assumptions. And even here in the Latin squares design, we need to check assumptions before we can go on and look at our interpretation. Now I'm going to be specifically looking at things regarding the treatment variable, but we can still we can make our error term, the residuals from the model. Now I'm going to use the car package. Remember, it has this QQ plot. I go back and forth, pick your favorite. You can also do QQ norm and QQ line, but I like the car because it gives this nice error bar that we can look at. I'll zoom in on this so that we can see this a little bit more clearly. Looking at the error bars and looking at my data are well within the error bars, so there's not enough evidence to determine a violation of normality. It looks okay. It doesn't look particularly great. I'm noticing these kind of breakdowns in terms of threes, not particularly uncommon given the model that we're running. All right, so normality looks fine. Let's check out homogeneity of variance so we can plot the fitted model against the residuals. This is our generic homogeneity of variance. This looks sufficiently random. There's nothing jumping out here as super off. We could also do those box plots. Now, specifically with this, again, because I'm not really testing these other factors and looking at these, I'm specifically looking at how homogeneity of variance is holding up within the groups that I'm looking at comparing. Now, this is an assumption about these other two, but remember the assumption relates to the statistical test. What I'm specifically looking for is making sure that each of my different treatment levels has relatively similar variance. Yes, absolutely. These all appear to be very, very close in terms of their relative variability, at least in the eyeball test. Again, we could follow these up with statistical tests, but even if the statistical test disagreed with the eyeball test, I'd probably still go with the image. So I tend to not do that. Ultimately, it's up to you. You could feel free to run those statistical tests at this time. And see your notes for descriptions of those. So now that we've passed assumptions, we can interpret. So now we're at the stage where we can finally run this summary of the model. That's what we've been looking up for so long here. And so we've got our different p-values. Now it looks like none of these p-values are statistically significant, but first I want to pause and make sure. So you notice up here I wrote in a little as-dot factor. Honestly, this is because when I was preparing for this video, I forgot to write the as-dot factor for these numbers, and the degrees of freedom turned out to be 1 for these numeric factors, these numeric blocking factors, where it was just repeating 1 through 3. So after noticing that, I remembered, oh yeah, I've got to write as-dot factor. So it's always important. I would always recommend checking these degrees of freedom to make sure they match. I've got 3 levels of driveway. I've got 3 levels for the factor operator, so I'd expect these to be 3 minus 1 or 2 degrees of freedom for each treatment, driveway, and operator. And in fact, in general, in Latin squares, I expect all of the degrees of freedom to be the same. And if you forget that as-dot factor, you'll notice that all of these degrees of freedom aren't going to be the same. In fact, you can go on your computer and try this out. Just remove as-dot factor and then come down and run this model, and you'll see how the degrees of freedom changes, and potentially even the conclusions change. So looking at this, the primary question I'm interested in, R asks these other questions. I'm not really interested in those. In fact, mentally I'm ignoring those because we normally don't test blocking factors. The primary question I'm interested in is, did the treatment work? And in this case, we do not have enough evidence to conclude that the treatment worked. So I'd write something like, we don't have enough evidence to statistically determine that the treatment worked at the alpha equals 0.05 level, or something like that. What I want you to notice is that looking at this image, it actually seems pretty clear that treatment A is better than treatment B and C. Right? So just the common sense, the no-duh look, it looks like A is better than B and C. So why is our statistic failing us here? And take a second to think about this. Why is our statistic failing us? Well, answering this question, honestly, the statistic is failing us because we don't have particularly many replications. We've only got these couple degrees of freedom in the error term. We don't have a particularly strong prediction. So with just 2 degrees of freedom in the numerator, 2 degrees of freedom in the denominator, our critical value for F is actually rather high because of the low amounts of degrees of freedom. If we bump up those degrees of freedom, the critical value for F falls. It's like if you flip a coin only 4 times to determine if it's a fair coin. Well, even if you get heads all 4 times, even if all of the observations in A are higher than B and C, even if you get heads all 4 times in 4 consecutive coin flips, that's not enough evidence necessarily to determine it's an unfair coin, right? We'd expect that to happen 1 out of 16 times anyway. So in this particular case, that's actually a great example of what's going on here and why, even though in the visual test it looks like A is just so much better than B and C, our statistical test isn't demonstrating that. This highlights the importance of replication in Latin squares, especially if you're looking to determine with a high degree of power a difference. And this size, a difference might not be large enough. Actually, if A were further away, these p-value would definitely be smaller. One more thing to consider here is the statistical significance of our two blocking factors. So remember, we really don't look at these, but in the randomized complete block design, we did mention that we could look at these in their variation components to determine how they relate to the residual mean squared. So in looking at these variation components, we can see that at least in the operator, which has a higher p-value than the driveway, it appears that this operator factor might actually not be particularly useful. Remember, when we add in a bad blocking factor, we artificially decrease the degrees of freedom without actually adding much or taking away much of the error variation, and that this can actually create power issues with our test. So if it turned out, and we don't have enough evidence here to make this determination, but if it turned out that one of our blocking factors was in fact not useful, that we shouldn't have added that blocking factor, that would be another reason why our statistical test might be underpowered, why our statistical test isn't demonstrating that, hey, it really looks like A is doing better than these other things. Even though it looks better, again, I want to caution you away from this, because even though it looks better, that's like saying even though, hey, you flipped 3 heads in a row on your coin, it looks like it might not be a fair coin. That's not enough evidence. Just flipping 3 heads in a row or flipping 4 heads in a row simply isn't enough evidence to make that determination. We need to gather some more evidence. This has been a presentation on how we implement Latin squares designs, including the randomization and analysis of Latin squares designs in R. In the next video, we'll talk about how do we incorporate other independent variables that we do care about in a process called factorial ANOVA.